So, ladies and gentlemen, welcome to this HKAE Hong Kong U Engineering Joint Tech Talk. We have a distinguished speaker today, Professor CHEN Guohua. Tech Talk is a series of forums and dialogues given by engineering researchers of diverse academic backgrounds to share their insights on innovation-related topics. So it's my pleasure to introduce our speaker today, Professor CHEN Guohua, who graduated from with a BEng from Dalian University Technology. I somehow feel very familiar with Dalian. He obtained his master and PhD degrees from McGill. I think I skipped the year. He's very young.
They can Google.
It's a shame. He had a national scholarship for that, and also received one from Canada. So he started his academic career in Hong Kong much earlier than me. 1994 in UST. I don't know which university you have not been. Polytech and CTU, all those years. And now he's back to HKUST. He serves as editor of a number of journals: Process Safety and Environmental Protection, Separation Purification Technology, Energy Material Device, and Energy Z. So he was the president of the 22nd International Meeting of Lithium Vice President of Council, IMLB. He's also the chairman of World Chemical Engineering Council. Very significant impact from our Hong Kong colleagues. He's a fellow of AICHE, HKAE, and he's also a fellow member of Canadian Academy of Engineering and Hong Kong Academy of Engineering. Welcome, Professor CHEN.
Thank you very much, Professor Lee, for the kind introduction. 各位恭喜发财. It's my great honor to stand in front of you today. Thank you for coming to my lecture here, because today I know everybody is busy, and energy storage is a topic we have been talking about for many years. And what's new? Well, I'll try my best to show you some electrochemical energy storage for current status and future perspective. And for the time limit, I will talk mainly about energy storage for power supply. Okay, so power supply means powering electric vehicles, electrical, in future maybe, flights, jets, things like that, or bikes. I will touch upon at the very end about the future for the grid energy storage. Okay, so as Professor Lee just mentioned, that this is the Hong Kong IE Tech Talk. I attended one the year before. It was delivered by our Hong Kong Observatory Director. It's quite interesting, and the topic, of course, talking about also something related to climate change. So climate change is real. Even though Professor Trump said something differently. So, well, this is the picture taken from NASA, and it shows that last year was the hottest year in our record history, and the year before was the hottest. So it means that according to the global average numbers here, so now we have where is the pointer? There's no, LED, you cannot show, okay, it's okay. So if you compare the color, yeah, yeah, simply compare the color here with the color bar here, you see, this is 0, and now we are somewhere here, okay, 1.2, something like this. And remember the Paris agreement. So what we really want by the end of this century, the increase should not be higher than 1.5. And the predictions nowadays said we were highly likely to overshoot 1.5. And if we do our work properly with all the government pledged and even carry out more efforts, then maybe we could reach this point, that is +2, by the end of this century. So we hope US would also play a big role. Otherwise, only China may not achieve this goal. And what is the source for the global warming or climate change? Basically, the emission of greenhouse gases. And greenhouse gases, the major contributor is from the energy sector. So almost 3/4. So the emission after that. And after that is agriculture, industry, and, well, from waste handling. In the energy sector, we're talking about energy use in industry and transportation, and also in buildings. In Hong Kong, this and this are the major contributors. Okay. And so what are the breakdowns for the emitters? Well, here you see the 5 lines. So this one, unfortunately, is China. So we are big. We are big in a number of things. And one of that is this CO2 emission. And from the beginning of this century until now, the trend for us is always growing. And another country that is India, it grows, but not as much as us. And other regions, they have a trend more or less the same or cutting down. We contribute over 1/3 of the emission. So in 2023, so we have 37.4 billion tons of the CO2 emission. So that contributes greatly for the global warming. And why China contributes this much and also grows? And that's because of population, energy, and also environment. And this is a global trend. From 70s last century until now, we see that the population grow beyond this, 7 billion, and by 2030, maybe beyond 8 billion, okay? And also economic development. We have the energy consumption, tons of oil, per capita. So what we see, this 70s there, we have 1.35. Now we are talking about 2.2. And if we want to see China's or our country's curve, some of you maybe just born after 85, so you experience this region. Well, a few of us were around this region. For a long period of time, we were not that much developed. So our emission for the CO2 were not that much. But after this, you can see that exponential economic development. And economic development requires energy. And more importantly, our energy source, you can see that is the coal, oil, and gas. That all fossil fuel. And only small amount is renewable, less than 10%. And good news is, so this is up to 2015. I tried to search updated data, but not available curve like this one. This is beautifully set. But recently, our GDP continue grow, not as deep as that. However, the primary energy source remains similar with more increase in renewable energy. So in the last 2 or 3 years, the new installation for energy, for power generation, more than half of that rely on renewable energy. So that's good news, okay. And globally, for the primary energy consumption is similar. You see the coal, oil, and natural gas play the major role, and with some hydropower, wind, solar, and then biofuel renewables. So that, on top of that, is less than 15% globally we're talking about. So renewable energy will be important in order to reduce the CO2 emission from burning of the fossil fuel. And also, we know that the fossil fuel are limited in their supplies. So for global warming combatment and also for the sustainable energy supply, we need the renewable energy. So China is in the right direction to develop more renewable energy supplies. And this figure, so I just copied this from, well, this publication is from Hong Kong U, your colleague, in the Nature Review, talking about global CO2 and methane emission. You can see that from 70 until nowadays, this trend is all increasing. And if we want to meet the target, okay, of 1.5, for example, that is a scenario for the increase against the pre-industrial level. We need to take sharp, dramatic actions. And even for 2-degree scenario, we need to have 4% per year cut down so that by the end of the century, we could achieve that goal. Okay, so that means that we need to really, analyze what would be demand. And so the demand for the consumption, in addition to the primary, we're talking about energy supply for this one. Electricity we're talking about here, you see, will be more and more as time goes because we can have renewable electricity. And the coal and the fossil fuel and the biofuel, all that will play some role, but the majority will be here. And the low carbon hydrogen will have some role to play. And this one, talking about changing of consumer behaviors to save energy. And also, we use more efficient devices, okay, in the, power storage transformation, things like this, okay? So, future smart energy system. Because of that, what for the whole system we will see in future? Well, we will have more power generated from renewables. And we will have centralized fuel production power and storage. And meanwhile, renewable can also be used for the chemicals or fuel generation. Of course, smart grid storage. That is important not to waste energy. Okay, smartly use that. And use the new energy electric vehicles. We have not only have a cleaner environment, but also we could have more efficient energy usage, okay? And what is the current situation? Well, this is the global EV outlook. of last year we talk about. See, for the past 5 or 6 years, we're talking about the increase for the car, EV car, is almost, see, exponentially. And auto back, and this one we're talking about the bus and big trucks, but they are available and not as much as this one. And the EV in Hong Kong, now we can see on the street, not only Tesla, BYD, and also other models. There will be even more. But in China, this is even more pronounced. Who are the producers of the EV batteries? And we are very happy to see that over 36% of that produced by CATL. That is our Chinese company. Okay. And the next one, 18%, also Chinese company. And the third one, below 10%, is from South Korea. And this is Chinese company, CALB, South Korea, and Japan, and China. Since we're talking about energy storage, about technologies and its development, even though this figure was strong, more than a decade years, and the trend simply shift a bit. And what you can see that from the very well developed pump hydro storage, now we have this one, this one, this one, and this one. This one we're talking about, lithium-ion battery. So that is already shift to somewhere here. Deployment and mature technology. Because for the LFP, lithium ferrous phosphate type of lithium-ion battery, now, so the industry seems I agree that it could be safely used for energy storage and also economically viable. This compares different kind of energy storage and also the time that we could use for this kind of technology for storage from seconds to weeks. We were talking about this supercapacitor. We could have the capacity range high, but it can only last less than a minute. You store it quickly and you use it quickly, and this one could be used to, as an intermediate energy storage for other long-term, if you want to have. And next one, this is mechanical flywheel storage and battery. Battery is versatile, depends on what type of battery you use. For the storage, could be from kilowatt to megawatts, things like this, from a few minutes to a few hours. So basically, normal design now, we're talking about 2 hours of sometimes maybe 4 hours, and not too long than that, mainly because the cost is still high. And flow battery can have longer storage, and also some more mechanical pump hydro here, and the last one here. For seasonal, from spring to winter or across the years boundary, you want long term, so could be used chemical energy storage. Simply convert electrical to chemical and then store the chemical, okay? And so this is a picture, this is a real picture for the, a solar power plant, and that is equipped with the energy storage. And in China, by law, it requires such a power plant to install energy storage from 10 to 20%. It depends on the region. Okay, so electrochemical energy storage for the new energy revolution we're talking about. for this end, everybody has at least one piece of battery and lithium-ion battery. And now electric vehicles. In future, some of those young researchers, you will drive EV, I think, more often than not. My next one will be EV, not this one. And of course, the large-scale energy storage, okay? Well, we talk about electrical energy and battery. Battery is not new, even though the application for the large-scale energy storage is new. So this picture, you can Google and find it out, that ancient Arabic, this is found near Baghdad. So something with the major components we can find for the modern battery. So the 600 BC. Yeah, our president asked me, do we have anything that is even more ancient? This is the one that is, we can have the sample in the museum. Maybe before that, there must be something that is maybe more primitive than this one and a longer time. But so far, this on record. So this is not something new. And so the search for the source of electricity that in the modern time start with Galvani. So, well, he was a surgeon actually, operating, was doing experiments and using, you see here, frogs, okay? And when he used the tweezer to touch the dead frog, you see the frog only leg, and he touched the top part and also the leg, and using the tweezer that made of iron and copper, what he found that the leg moves. So his conclusion was a frog's leg will respond like alive when touched by the two different metals, and see the leg of the frogs has electricity generating power. That is his conclusion. So electricity produced by this muscle of the frog. And somebody did not believe that, so that was also an Italian, and he's a physicist and a chemist. We know him very well. In our middle school, we know this word. Yes, that's right. Yes, yes. And what he found, is, for the experiment, it has the leg, has the metal, another metal. And he said, the electricity is produced by the different metals. If you use the same metal tweezer, you will not have electricity. And different metal, you have that. And he made the first pair of electrochemical cell. And this one is available in Walter's Memorial Hall in his hometown. It's a small town, Como. If you visit Milan, if your time is flexible, I recommend you to take train and spend one day there. And this town is a beautiful town with beautiful lake, with Alps and snow-capped mountain not far away. And when you get out of the train station, you will see huge statues. At the beginning, I thought, oh, who is this? And I read, the name, Volta. Okay, that's his hometown. Okay, so and his hometown built the memorial hall for him. Okay. And the further development for the rechargeable battery, that is the lead acid battery. This probably is most used battery for rechargeable or usage before lithium-ion battery. So what we see here, the chemical is very simple. Lead oxide, lead, and lead sulfate. And so this could be, charged quite a number of times for most usage. For example, in our car, not EV, normal car. That's right, to start a car. The plug spark is generated by this type of battery. And for most of the UPS, still we use this type of battery. But why this type of battery is not used for the power plant? Because first, it's capacity. Second, for power plant, charge-discharge service life demands beyond its capacity. Okay. And, well, in fact, when the lead-acid battery was first commercialized, and this EV was built with the batteries. And that was 1899. And during that time, this car, of course, everywhere, is battery except the wheels and the seat. It can run at that time. I can compete with the internal combustion engine. But later on, internal combustion engine, of course, developed much faster, and the battery development was not that quick. So we dropped until 10 or 15 years ago that EV pick up again. And this one, is the battery for the phone. And this is the antenna of the phone. You can see now how convenient we are. But at that time, I think he is also very proud. I have battery. I have some phone that could talk remotely. Well, yeah, this is just general expression, comparison of the different kind of battery from the lead acid, nickel, calcium, and also nickel metal, lithium battery, polymer lithium battery, and lithium battery. And see, this is at the very beginning of the century, 2001, and a paper by Professor Taras Khan. And he noted this, lithium metal battery unsafe at that time. Okay, and I think this unsafe is still true if we do not have proper chemical treatment for the lithium metal. If we have proper treatment for the anode, we could make it safe. Okay. And well, unsafe because we're talking about the birth and death of lithium batteries. So in the 70s, the Vietnam that found using this chemical, titanium sulfide, the lithium can get in and out. We call it the, in and out of the, between the layers in the space. And encapsulation and we call it lithiation, delithiation, this kind of chemistry. And later on, this is made use together with the metal, lithium metal as the anode, and that as cathode, and they made the commercial product. And the problem is, after maybe 10s, 20s of, depends on how you use it. So the lithium could deposit and strip, deposit, strip, but deposition of the lithium could have this dendrite formation. If this dendrite formation is so big and so strong, and it can penetrate through the separator and contact the cathode. Anode cathode contact, then you got short circuit. Short circuit means a large current and thermal runaway explosion. And because of this safety issue, so this is the end of the lithium metal rechargeable battery. So after this, company, of course, lost a lot of money, and they call back the products. People thought maybe we'll say goodbye to lithium battery. Remember, this is lithium battery. Okay, so this anode is made of lithium metal. However, later on, somebody found, that is Akira Yoshino. He found if we do not have a plain, current collector or lithium, we have graphite. And lithium can also get in between the layers of graphite and out, in and out. On the other side, of course, we could have even better material, for example, lithium cobalt oxide layered structure. So charging and discharging, charging, discharging, this, just like this side, you have type of bird net. And this, you also have bird net. Birds can fly this way or that way, depends on where the, food they can find. And this make the battery much safer, because if you look at carefully in the electrolyte, you only see lithium iron. And here you do not have lithium metal. There, of course, you do not have lithium metal. So this kind of battery we call it lithium iron battery. So now, the batteries we are using all are in this form, lithium iron battery. And the difference is whether or not they use cobalt oxide or magnesium or NMC or lithium ferrous phosphate, things like that. Or this side, they could use some other type, silica or silicon or special kind of a structure for lithium insertion, okay? And for lithium cobalt oxide, credit goes to John Goodenough, who found this chemical. And for this one, well, of course, credit goes to Yoshino. Yeah. And remember that before, we have this person here, Whittingham, found the chemistry, insertion, and extract out of the layered structure without changing the physical in and out, and there is a electrochemical redox reaction happening in place, but the structure can be maintained. So this kind of chemistry goes to Whittingham, and anode, cathode, major parts of this battery goes to John Goodenough and Akira Yoshino. And after that, starting from here to here to here, that is more than 30 years development. More than 30 years development, and they got deserved Nobel Prize, 3 of them. And this person, when he got Nobel Prize, do you know how many years old? More. 100? Low. You said that you got the range right. 97. Whoa. He lived until 101. When I was in UST, at that time I was the head of department, 90s, early 2000. During the Nobel Prize time, some reporter, local journalist, called me, can you prepare paragraph 2? If John Goodenough got the Nobel Prize, we can use it. I said, okay, I can prepare something for you to use it. But we did that for a few years, and then we dropped it. We thought, no way he could got it. Not good enough. Until he's 97, so 2019. But, well, this is a good story. This is for science. This is really for material development and also device deployment. For such kind of technology or scientists to get Nobel Prize, it's not easy. It's a proven beneficial to the society. So if we do not give to him, people will feel sorry. So 2019, he got it. Okay. Yeah. Another thing is we need also to live a healthier, longer life. If you want to aim for Nobel Prize.
Just wait.
Yes. Yeah.
Change the name from good enough to long enough.
Long enough. Yes. Long enough. Old enough. Okay.
Old enough.
Yeah, old enough. But these stories, he is an electrochemist, a physicist. He started working on battery materials after 60s. After he already, older than me. So if you want to do something new, never too late. Okay, never too late. But you have to find the right direction, of course. Yeah, and also he moved from Oxford to USA, Texas, where he does not need to retire. And also his payment there is relatively okay. So he does not need to worry about financial situation. And he worked happily until 101. Okay? And during his 100 years birthday, there was a conference organized in his honor at Texas Austin. I was there also. He was not that well during that period of time. And he momentarily showed up during the banquet. But unfortunately, I left before the banquet. But I had communication with him. Something to do with Professor Zhang, my Tarascon. Tarascon is a person, if we could have another one, so Tarascon could be the one here. And so that's a very interesting story to share. And for the other two, I have personal contact with them. So we might frequently during meetings. This is after his Nobel Prize. I had one also before his Nobel Prize. And before his Nobel Prize, he did not believe he would get it. So when we joke with him, when you got Nobel Prize, we share the money. Yes, of course. Here, I asked him, how do we share? He said, no, my wife took it. So, already. Yeah. He was here in Hong Kong when I organized the IMB. He is one of the plenary speakers. We gave him half an hour. He took more than 1 hour. He had a talk and had a show, but everybody likes to listen to Nobel Prize winner's story. He gave a good talk. Yeah, he still works. Yeah. After his talk, he left for Shanghai. I asked him, why you don't spend a few days in Hong Kong? We could show you around Hong Kong. And I need to go to my company, Shanghai. Yeah, so. Well, let's go quickly. For those non-expert in the field for battery, see that major component of battery, you have anode, cathode, separator, electrolyte. That's the 4 major components. And what require for the device, you need to have cheap, safe, stable, and high capacity, of course. So if you could make things like that, then there is a future. How can we achieve that? Of course, material synthesis or material modification. If somebody had some material, well, you can modify it and have it with such kind of capacity, okay, or features, okay. And basically, for the cathode part, we start with LCO, NMC, LFP, LMO, and also we have lithium, sulfur, lithium, oxygen. And anode side, more often than not, we have graphite. And now we also have some silicon carbide because of the capacity. And this is because of stability and for long-term service. And lithium metal come back again. Okay, so resurrection of the lithium battery, okay, with the lithium metal as the anode. And what is the drive for the development for those materials? Basically, you can see consumer electronics, we're talking about the power density 100 or maximum 200 be sufficient. And for EV, we're talking about 200 to 400. Now, with the NMC, we could achieve this if we do things right, okay? But in future, so we are really talking about, flying objects, so the power energy density will be much beyond this 600 watt-hour per kilogram, okay? Yeah. Okay. So another driver, why now we have so many cars on the street? Because people can afford it. You see the price from the early of 2013, that package, you're talking about 1 kilowatt hour using the standard 2024. So that is over $800 US. But now it's slightly above $100. But in China, this is already dropped below $100. So Chinese, well, we should be proud. We are the major driver for the manufacturing so that the price of the battery pack price dropped. You see, in 10 years' time, from 800 to below 100. Okay, demand for high power energy and also drop of the price. Okay, and so the market, because of that, we could have lots of electric vehicles running on the street. You see the Chinese market, so BEV, the battery EV, and plug hybrid EV, and here we're talking about much over 50% globally, okay? And the next one is Europe, and then US, and the rest of the world, okay? We are leading the world in the EV, and also, you can see that this is about the cathode material. What are the material people use? For example, China, we use LFP, lithium ferrous phosphate, more, okay, because it is safer. And BYD is the major driver of that. And the next one is the high nickel content NMC. So because of high energy density. And for Europe, they have more of that. And LFP they do not have that much. It's not because Europe cannot produce it, because Europe does not have the patent to produce it. China has the patent to produce FFP. And United States, they use this also. And the FFP development, because of A123 got bankrupted, cannot compete with China. And now we are leading the world in this, and also now competing in this area with them. Okay. FFP, that's lithium ferrous phosphate, NMC, that is nickel, magnesium, cobalt. The trend development, this is from a German organization that predicts. So talking about here, that is the trend for its deployment. And so different region for Europe, China, Japan, Korea, US, you can see the share. And China, now we are the major player. Eventually, the other parts of the world would cut in. But still, we have large share of that NMC. And also for the LFP, we will remain the major player. It's not only because we have already installed manufacturing of LFP, but also those companies, CATL, Gotion, and also BYD, they are producing such kind of batteries in other parts of the world, okay? So they will meet the demand from the other parts of the world. And well, this is a figure that I got from Professor Jean-Marie Tarascon, basically telling similar story, but in more details. If you're interested in this, take a picture and study it more details. Okay. Yeah, thank you. And here we're talking about share manufacturing capacity by the producers domicile. We're talking about, you can see China, of course, the products we use, most of that is produced by us. Okay, small amount by the Europe or by US, Japan. But in Europe, so we have now small part produced by Chinese. And we will see by 2030, we'll be increasing produced products by Chinese. And the next one will be Korea. And this one will be Europe itself, okay? US may have some, okay? But the rest of the world, say we're talking about, say for China's market will increase. But I think this is a conservative prediction because the investment of Chinese manufacturers are really high. And maybe by that time, we will have something like beyond 20%. Okay. And so what are the materials, the new materials? Say if we could look for future development. And here I compare the cathode material that for their capacity, and this one using anode of graphite. This is based on the lithium. And anyway, you can see. So this, we're talking about, see, LFP, LCO. And this one, we're talking about NMC. And this is LVPO and LMO. And this is 811. It's a high nickel content. And what we want when we combine that with the lithium metal, and you see, this one, and also, of course, this one, the capacity would be much higher than that. And in future, we'll see more of this. in the market. Okay, high nickel content NCM. Okay, and also when we're talking about the analysis based on the voltage, cost, energy, power, cyclability, and safety, and you can see that lithium-rich layered oxide, if we could improve the cyclability, and this would come up, okay, with a big player, okay. Nickel-rich layered oxide also, okay, first two of that, okay. And why, NMC has high capacity but does not compete well with LFP because it has a few issues. For example, poor thermal stability, and also the surface degradation can get easily have the electrolyte oxidation, CEF formation like that, and also poor structural stability. At the beginning, you have something like that. After, hundreds cycles, you have the micro cracking, so that the particle would get polarized. And transition metal can also be dissolved into the electrolyte, and that cross over to the anode, and then the service life, safety of the battery will also be affected. Okay, and how can we do that? So remember that material is good, but it has some issues, so we could modify the material to remediate such kind of problems. For example, we could have a larger particle rather than small with a secondary, or we could have doping, so that the doping could make the structure different, or we could have a different kind of concentration, because high nickel at the center and lower nickel at the outside more stable, things like that, or have core shell structure or surface coating, or the surface treatment by such kind of material washing. Okay, basically it's to change the surface property. So in my lab, I have done this one and also this one. So I will show you a few pictures quickly. NCM particle morphology change by doping. We have the titanium doping and also niobium doping. And after doping, basically, without doping, you have the shape like that. But after doping, we would have longer, needle type of structure. And then after that, you see the performance comparison. This is without doping, and that is with doping. Without doping, with doping. So with doping, we can significantly improve the performance. Okay, and half cell, full cell tell the same story. And so this is further looking about how it can mediate the bulk structure. This one without, this is with, so the cracking is significantly suppressed. And this is a more detailed study. Say the doping can also improve the electrochemical performance. So this H2H3, peak shift, it's more reversible. And this one you can see is not that reversible. Okay, and this is a further STEM sample looking and see what is the change of the structure morphology. Okay, and next one is coating. Okay, so we coat very thin. Maximum we're talking about 28 nanometer, or 20 nanometer. 20 nanometer is what kind of dimension? Our hair is 50 to 80 micrometer. That is 50 to 80,000 nanometer. That's our hair diameter. So this is a really thin, very thin layer of polymer, conductive polymer P-dot coating. And what is the effect? Say without coating, that is the cycling performance. Means that at the beginning you have this capacity. After 200 cycles, you drop that to less than half. But after coating, there is still some degradation, but not that much. And well, I'll skip this one. And you see that without coating, you have the cracks. With coating, not. And the reason, because our CVD type of coating, see, not only we coat the outside, but also the vapor can get to the inside of the particles. So the boundary of the particles all well coated, instead of only the outside surface like most other coating. This is the reason, okay? Well, that's other things, the new playground for designing high-capacity electrode. So that is from Professor Jean-Marie Tarascon last summer. He gave a lecture in UST. So I asked him, I found your talk is very inspiring. Can I borrow some of your slides? He said, okay, you are welcome to use it. You can see that, there are more type of materials in future for us to explore for the students. You could, notice of that. And the major part of this, of course, capacity, safety, and also cost. Okay, so, and more of that we're talking about is we try to get the power, energy density from 500, double that to 1,000. And what would be the possible milestone we're talking about? Now we are using this, and this one. And lithium-rich layered oxide may take us there. Okay, so this is one thing. And another thing to note, so for all the current used battery, we only focus on the, cationic redox, from the cathode. And now the cathode material is not only the cationic and also anionic redox could make contribution. And with that, we could reach to this part. And of course, there are quite a number of issues, release oxygen, low energy efficiency, things like this. So, and there are some ways to overcome this, but of course, it's not perfect and not ready for industrial deployment. For example, we could synthesis using air exchange reaction, but that could make the cycling more stable. Or we could have a precursor, have this oxygen deficiency. And when oxygen release, the deficiency part will take it, so it will not have the structure change. So this is, before it's like that, afterwards it's like this. So cycling performance, you can see that significant change. Or we could make more doping using fluoride, okay, here. And with the fluoride, this is the work from Jean-Marie Tarascon's group. So you can see the change in terms of voltage, capacity, and also energy density, okay? And so next, they're talking about the new anionic redox reaction we mentioned. Anionic redox could also play a role so that we could have a capacity from 150 to 280 milliampere hour per gram, okay? And so this is another, So lithium sulfur, I must talk about this. This is the resurrection of the lithium metal, using lithium metal as the anode, sulfur as the cathode. It has very high capacity, theoretical capacity we're talking about, 2,600 watt-hour per kilogram. And also the sulfur is abundant, it's very cheap, and tolerance of over voltage and low cost and environmentally benign at this time, okay? And the problem, fundamental problem we're talking about, that's the organic electrolyte used, flammable one, and poor cycling performance and safety issue caused by the lithium dendrites. Still problem, but after 30-some years of study, development, and we have some ways to overcome this. And low sulfur utilization means that we need, because sulfur is not conductive, we need to add more conductive materials in order to make full usage of sulfur at the cathode. Okay. And so strategies to meet the challenge of such kind of battery could, from the cathode part, electrolyte, separator, and also anode. And all that could help, okay? And so state of art of that, I'm not going to talk about the details. If you work on that, yeah, take a picture, good. Okay. In fact, I have a review paper published in the EER the year before, and that is on the challenge and the opportunity of lithium sulfur battery. And that was selected as the best paper of that year. And this is some work done in my group, talking about the anode and cathode part, and also the separator part. For the anode, lithium anode especially, how we design the power collector so that we would delay or suppress the dendrite formation. Okay. And this one, so I borrowed from Professor Ouyang Gao. He is supposed to be the leader for battery or energy storage in China nowadays. He is a professor from Tsinghua University. He used to work on fuel cell powered vehicles. And now his more effort is on battery. I asked him why you changed from fuel cell to battery. Well, he said he made a demonstration for fuel cell. But for fuel cell to make money, there are still years. How many years? He could not see. Maybe 10 years later. 10 years later is more important. So, but for battery, it's already in use. And if we have good technology, we could make it commercialization and benefit society. And what this figure in his new book predicts, so by the middle of the century, China would have 400 million vehicles. Those 400 million vehicles, if we're talking about each one carried average 50 to 70 kilowatt hour battery. So that's a huge amount, 24 billion kilowatts electricity in EV. So that EV will be a very valuable source for energy that storage with the grid. Okay, so V2G at that time would have a huge market. So in one of his lectures I attended, he said, after this picture, there will be more than 10. We're talking about $1,000 billion business. $1,000 billion. $1,000 billion, and I think in Hong Kong, Li Ka-cheng is close. And Mr. Zheng is close. So after of this, there will be 10 of such kind of business, okay, in China. And around the world, there will be even more, okay? And I did not mention about this. And for the low, we're talking about the attitude economy. So there will be also huge amount of money to make. And also is coming, okay? So with that, I conclude. I think you agree with me on that. We're talking about huge market. We're talking about demands, low price, long stability. And the EV with high capacity battery will replace ICE-based vehicles. And in Europe, at the beginning, they banned ICE, but now they relax a little bit. If they burn renewable liquid fuel, it's fine. But still, that is a limited amount. And also this will be, EV will have huge market there. And EV would support grid, energy storage, low altitude economy. I did not have time to talk about safety. Safety is number one issue, basically. If your battery is not safe, nobody will buy it because nobody dare to really bear the consequence of the accidents, because the accident, large scale, will be quite catastrophic. So safety, how we achieve that from material design, from safe, selection of the materials, electrolyte, and also operation, battery, or energy management, all that would be important. Okay, so with that, I thank you for your attention. Okay.